In the middle of peak growing season, trucks pulled up beside flooded rice paddies and released thousands of ducks directly into fields that had been treated with chemicals for years. No fences separated them from the rice. No protective barriers guarded the young plants. Just water, seedlings, and moving flocks spreading across the surface. From a distance, it looked careless. China produces nearly 28% of the world's rice. That means what happens inside its rice fields affects global food supply in a very real way. Over the past decades, chemical fertilizers and pesticides helped increase yields dramatically. But they also left scars. China uses roughly 4 million tons of pesticides every year, and rice farming is one of the most input-intensive sectors. Over 40% of Chinese farmland now shows measurable soil degradation. Organic matter has declined. Beneficial microbes have weakened. In some provinces, pesticide application rates reached 2 to 3 times global averages just to keep harvest levels stable. The system was still producing rice, but it was losing strength underneath. This is where the shift began. Instead of increasing chemical input again, some farmers and researchers turned to an older method. They reintroduced ducks into the paddies not as decoration, but as active participants in the ecosystem. This approach is known as integrated rice duck farming, and it has existed in parts of East Asia for centuries. At first, the idea sounded almost symbolic. Ducks walking through fields treated with industrial chemicals did not seem like a modern solution. Yet the decision was not random. It was backed by long-standing agricultural knowledge and growing concern over the limits of chemical-intensive farming. Modern rice cultivation depends heavily on synthetic fertilizers, insecticides, and herbicides. These inputs helped fuel the Green Revolution and dramatically increased output. But they also altered soil biology. Pesticides reduce not only harmful insects but also beneficial organisms. Fertilizers create nutrient spikes that disturb natural cycles. Over time, farmers must apply more chemicals to achieve the same result. When productivity rises but resilience falls, something is wrong beneath the surface. Agriculture accounts for roughly 20 to 25% of global greenhouse gas emissions. Rice paddies contribute significantly because flooded fields create anaerobic conditions. In these oxygen-poor environments, microbes produce methane as they break down organic matter. Methane from rice cultivation alone accounts for around 10% of agricultural greenhouse gas emissions globally. At the same time, nitrogen runoff from fertilizers contaminates waterways. Soil microorganisms that once maintained nutrient balance decline. Organic matter levels fall season after season. What appears efficient from above often hides imbalance below. More than half of the world's population depends on rice as a staple food. If rice ecosystems weaken, the consequences ripple across entire regions. That context makes the duck release more than a local experiment. It was a response to a system under pressure. The rice duck model itself is not new. Historical records show it has been practiced in China and Japan for over 600 years. Farmers would introduce ducks into paddies about 2 to 3 weeks after transplanting rice seedlings. By that time, the stems were strong enough to tolerate movement in shallow water. Timing is critical. If ducks enter too early, fragile seedlings can bend or break. If introduced too late, pests and weeds may already be established. Research indicates optimal duck density ranges from about 150 to 300 ducks per hectare. Fewer birds produce limited biological impact. Too many can cloud the water excessively and stress the plants. The system depends on balance, not volume. Once inside the fields, the ducks do what they naturally do. They forage. Brown plant hoppers, stem borers, leaf hoppers, mosquito larvae, and various aquatic insects become immediate targets. These are the same pests farmers typically control with chemical sprays. Within weeks, pest populations in monitored rice duck systems have been observed to decline significantly. In some studies, pesticide use dropped by 50 to 70% compared to conventional fields. The reduction is not a one-time event. Continuous movement disrupts pest life cycles before they reach outbreak levels. What looked chaotic was actually biological control in motion. Weeds face similar pressure. Ducks consume young weed shoots, such as barnyard grass and duckweed, which compete directly with rice for nutrients and sunlight. Their movement also disturbs weed roots before they can form dense mats. As a result, herbicide dependence decreases. But pest and weed control are only part of the transformation. As ducks move through the flooded paddies, they constantly stir the top layer of soil. This agitation introduces oxygen into the shallow water and upper soil surface. Oxygen reduces anaerobic conditions, which in turn suppress methane-producing microbes. Field research has recorded methane emission reductions of roughly 20 to 30% in rice duck systems, compared to chemical-intensive paddies. At the same time, duck droppings distribute organic nutrients evenly across the field. Unlike synthetic fertilizers that deliver nutrients in concentrated doses, duck manure releases nitrogen and organic matter gradually. This steady nutrient flow improves soil structure and microbial activity. Studies have shown that integrated rice duck farming can increase grain yield by up to 15 to 20% compared to monoculture systems without ducks. Improved phosphorus availability and enhanced microbial processes contribute to this gain. The field does not simply survive with fewer chemicals. It often performs better. Beneath the waterline, the system begins to repair itself. Soil organic matter improves. Beneficial microbes recover. The need for chemical correction decreases. Instead of forcing the ecosystem with synthetic input, the biological interactions start doing part of the work. The transformation does not happen instantly. It unfolds over a growing season, but the shift is measurable. Lower pesticide bills, reduced fertilizer use, stabilized yields, lower methane emissions. Thousands of ducks moving through chemical rice fields were not a symbolic gesture. They were a functional intervention grounded in long-term agricultural practice and supported by modern research. The decision was not about rejecting technology. It was about restoring interaction within a system that had become chemically dependent. And the results were not theoretical. As the season progressed, the results became visible in ways farmers did not initially expect. Water clarity improved. In many conventional paddies, heavy fertilizer use encourages algae growth and creates a murky surface layer. In rice duck systems, the constant movement of ducks disrupts excessive algae buildup. Oxygen levels increase. The smell associated with stagnant anaerobic conditions gradually fades. Small signs begin to appear first. Dragonflies return. Frogs reappear along the edges of paddies. Small fish are spotted moving through channels that had previously felt lifeless. These are not dramatic changes. They are indicators that biodiversity is rebuilding. The rice field starts functioning as a living system again, rather than a single output production surface. The recovery was ecological before it was economic. But the economic shift followed quickly. When pesticide use falls by 50 to 70% and fertilizer requirements decline by 20 to 40%, cost structures change immediately. For many smallholder farmers, input costs represent a large share of total production expenses. Reducing chemical purchases directly improves margins. In some monitored regions, total input cost per hectare dropped significantly in the first growing season. This reduction does not depend on market fluctuations. It comes from spending less money up front. At the same time, rice grown under rice duck systems is often classified as ecological or low-chemical rice. In urban Asian markets where food safety concerns are high, that label carries value. Studies and agricultural reports indicate such rice can command 10 to 30% higher prices compared to conventionally grown grain. Lower costs combined with premium pricing shift the income equation. The ducks were not just saving soil, they were changing farm economics. There is another dimension to the model that strengthens its financial impact. The ducks themselves become a secondary product. Raised in open paddies with natural feed sources, they grow with reduced reliance on commercial feed and minimal antibiotic intervention. At the end of the season, farmers can sell duck meat or eggs as an additional income stream. This diversification spreads risk. If rice prices fall, duck sales provide partial protection. If duck prices fluctuate, rice remains the primary crop. The land produces two outputs from the same space without requiring separate infrastructure. In some cases, revenue from ducks offsets a large portion of rice production costs entirely. An ecological method transforms into a dual income system, but the long-term environmental implications may be even more significant. Methane reduction in rice duck systems is not a minor detail. Methane is a greenhouse gas far more potent than carbon dioxide over shorter periods. Flooded rice paddies naturally produce methane under oxygen-poor conditions. By stirring water and introducing oxygen into the upper soil layer, ducks disrupt methane-producing bacteria. Field studies comparing integrated systems to conventional paddies have recorded 20 to 30% reductions in methane emissions. When applied across large rice-growing regions, even partial adoption could contribute meaningfully to agricultural emission reduction targets. This is not a theoretical environmental claim. It is a measurable climate impact. The system was reducing emissions while maintaining yields. As soil health improves, organic matter increases gradually. Improved structure reduces compaction. Root systems penetrate deeper. Nutrient retention becomes more efficient. Instead of applying increasing fertilizer doses each season to compensate for declining soil performance, the ecosystem begins to stabilize. This is the principle behind regenerative agriculture. Rather than extracting productivity until degradation forces intervention, regenerative systems aim to rebuild biological cycles continuously. However, the rice duck model is not a universal fix. Precision matters at every step. Ducks must be introduced at the right growth stage. Typically, that means 2 to 3 weeks after transplanting. Too early, and young seedlings can be damaged. Too late, and pest control becomes less effective. Removal is equally critical. When rice enters the panicle initiation stage and prepares to flower, ducks must be withdrawn. Even minor disturbance during this sensitive period can affect grain formation. Density must also be managed carefully. Research suggests 150 to 300 ducks per hectare is optimal under most conditions. Below that range, pest suppression weakens. Above it, water turbidity increases excessively and plant stress may rise. This is controlled biology, not random release. The method works, but only under disciplined management. There are also structural limitations. Fields require stable, shallow flooding to support both rice and ducks. Regions with inconsistent water supply struggle to maintain ideal conditions. Heavily polluted soils may not respond immediately to biological restoration. Steep terrain complicates flock control. Predators present another challenge. Snakes, foxes, feral dogs, and birds of prey can cause losses if flocks are not monitored. Labor requirements differ from industrial systems, while chemical spraying reduces the need for field supervision. Rice duck systems require ongoing observation and water management. In areas facing rural labor shortages, that becomes a barrier. These limitations clarify something important. The rice duck model is not a replacement for all forms of modern agriculture. It is a context-dependent system that performs best where environmental conditions, labor capacity, and water control align. But where those conditions exist, the results challenge a central assumption of industrial farming: that higher chemical input is the only path to stable yields. In China, releasing thousands of ducks into chemical rice fields did not cause collapse. It triggered recovery. The experiment demonstrated that productivity and ecological restoration are not mutually exclusive. A system long treated as fragile responded positively to biological integration. The deeper lesson extends beyond rice paddies. Modern agriculture faces rising input costs, soil degradation, climate, pressure, and biodiversity loss. Scaling production through chemical intensity alone increases financial and environmental risk. Systems that combine productivity with ecosystem repair offer a different trajectory. Sometimes innovation does not mean adding complexity. Sometimes it means reintroducing relationships that were removed. The image of ducks walking calmly through flooded rice fields may look simple. Yet beneath that surface, pest cycles are interrupted, methane emissions decline, soil microbes recover, and farm income stabilizes. What appeared outdated turned out to be resilient. And resilience may be the most valuable resource agriculture can build in the decades ahead. Hit the subscribe button and turn on notifications so you don't miss the next deep dive into the systems quietly reshaping our world.